Now, let's integrate our gas law concepts more deeply with past material by considering stoichiometry in gas calculations. So gas can be a reactant and/or a product in a reaction. And so we can treat calculations in a similar manner as we saw in Chapter 4 for the relationship between moles of products and reactants in a balanced equation. When solving these kind of problems, we simply apply the mole fraction partial pressure approach of Dalton's law. For example, if we have 1 mole of nitrogen gas and 3 moles of hydrogen gas reacting to produce 2 moles of ammonia gas, we have a relative N of 4 equivalents on this side and a relative N of 2 equivalents of gas on this side. So if this reaction were carried out in a vessel of fixed volume, because pressure is proportional to N, the pressure, once the reaction is complete, will be 1/2 the starting pressure. So let's see some examples. In the first example, I'm going to consider the reverse reaction. In this case, we have 25 grams of ammonia, that's NH3, as a gas at 255 degrees Celsius in a 1-liter vessel, and it decomposes to hydrogen gas and nitrogen gas. Now, assuming that the reaction proceeds completely to products, what will be the total pressure inside the vessel after all of the ammonia has decomposed? Here, assume ideal gas behavior for all species. To solve this, we have to consider that we're given a mass of ammonia that we start out with, and we have to figure out how many moles that is. So, first, let's take our 25 grams of ammonia and divide by the molecular weight of ammonia, which is 17.0306 grams per mole of ammonia. It's important to identify the species when working with reactions like this, because in the next step, I'm going to consider the stoichiometry of relative hydrogen gas formed from 25 grams of ammonia. So I want the stoichiometry of ammonia down here, moles of NH3, because I want these factors to cancel out. And for every 2 moles of ammonia, there will be 3 moles of hydrogen gas generated. And we are left with 2.20, how many significant digits do we have? 3. 2.20 moles of hydrogen gas. Next, we have to do the same calculation for the nitrogen gas produced. So we have 25 grams. Once again, the molecular weight of ammonia is 17.0306. And our stoichiometry is 2 moles of ammonia react to give us 1 mole of nitrogen. And when I complete this calculation, I get 0.734 moles of nitrogen is produced. And finally, since we want to know what the pressure will be inside the vessel after all the ammonia has decomposed, we calculate P equals nRT over V, and we sum our pressures over here, our moles over here, plus 0.34 moles and 0.08206 liters atmospheres per mole Kelvin. It's our ideal gas law constant. Temperature is 255 plus 273.15 Kelvin over the volume, which is 1.000 liters, and our answer in this case is 127 atmospheres. Now, because we have calculated the moles of each product separately, I could give you the partial pressure for each of these by summing 2.201 moles with 0.734 moles to get 2.935 moles. And then I can calculate a mole fraction here, 2.201 divided by 2.935 moles of that gas divided by the moles total times the pressure of 127 atmospheres. And I can tell you then that the partial pressure of just the H2 gas is going to be 95.2 atmospheres. And the partial pressure of the other is going to be, we could calculate it out, but it would be 127 minus this value, or since the two have to add up to 127, and that is 31.7 atmospheres partial pressure for each of these. The question, as I originally phrased it, didn't ask for the partial pressure of each product. It asked me to stop here. But I just showed you that because we calculated these out separately, we can actually calculate those partial pressures if it were required by the question. In theory, we only really needed to deal with the stoichiometry, the fact that we have 2 moles of gas becoming 4 moles of gas, and we could have treated this question by simply assuming that we begin with 25 grams of ammonia and calculating the mass like that for ammonia, and then calculated that we have for every 2 moles of ammonia, we have 4 moles of product. This would also give us 2.935 moles of product, and then we could have plugged that in down here as well. Note that this alternative way of solving it up here is less work, but does not allow us to rapidly calculate the partial pressures of each product if we were required to do so. In this problem, we're asked to calculate the volume of carbon dioxide at 1 atmosphere and 298 Kelvin room temperature released from a car's engine upon combustion of 60 liters of gasoline. So here we see that gasoline, a liquid, reacts with oxygen to produce carbon dioxide and water. To solve this, we first need to figure out how many moles of gasoline we started out with. So, if we have 60 liters of gasoline, to get to moles, we need to first convert to grams, and so we have to consider the density of gasoline as 770 kilograms per liter, and then convert kilograms. We get 404.45 moles of octane gasoline. And now the moles of carbon dioxide is going to be this value times the stoichiometry change. So we do our dimensional analysis to treat 1 mole of C8H18 being equivalent to 8 moles of carbon dioxide in the conversion. And we get 3,235.6 moles of carbon dioxide. Finally, we use V equals nRT over P, and we plug in our 3,235.6 moles of carbon dioxide, and R, the temperature, and divide by the pressure. And the final answer is going to be 7.92 times 10 to the 4th liters. Before I finish, I want to point out that we had stoichiometries in this problem that we did not actually need to use. We only really need to think about the fact that 1 mole of octane, or gasoline as we're calling it, is converted to 8 moles of carbon dioxide. I hope this helps you solve stoichiometry problems with ideal gas laws, because you will be seeing these on a test at some point.